Hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In this particular discussion, we're going to look at a way of representing internal energy of a system in the form of a partition function. And of course, this is going to be a follow-up discussion from my initial discussion on the concept of the partition function. Now, I mentioned basically that all the thermally accessible energy levels of a given system, or the number of thermally accessible energy levels of a given system at a particular temperature, is basically the concept of or represent this concept of a partition function. And of course, they represented in terms of this specific initial given as Q, and therefore they defined Q in terms of an algebraic representation or a formula whereby it said that this represents all the thermally accessible energy levels of a system, whereby we are given it in terms of an expression, whereby this was given as an exponent over U given as such. And in this case, I defined this aspect of this specific notation, whereby I said this one represents the inverse of the product of Boltzmann's constant and the absolute temperature given as such. Now, in this case, I'm going to basically be using these two formula interchangeably. Now, in this case, we need maybe to define some of the variables which are going to be found using this specific denominator for kdt, and I sometimes going to use this specific initial for brevity. So in this case, I'm going to have this one still represented in terms of all the levels. Now we're going to consider the use of standard integrals in this case, and I'm going to substitute it with this in some of the cases whereby we're going to need to create clarity. So this still is given in terms of a negative that specific energy, and then we're going to have kBT given as such. So these are two basic representations for that specific particular partition function which are given in my initial discussion. Now, the concept of internal energy can as well be given in terms of the partition function, whereby, as I had said, we are going to represent this one in terms of U, and this is going to represent the summation from the initial state of this thermally accessible levels, and this is going to be having this symbol, and then we shall have this one given as the internal energy of that specific system, and the exponential notation given as such, and this is going to be given as over kBT. So this is an division or an over sign given as such, and this is going to form part of so the exponent of this negative energy over kBT is going to form our numerator, and I'm going to have this one divided by Q given as such. So basically, a variation of this specific representation for the concept of a partition function is going to form our numerator in this specific case. Now, if we try to look at this one, and therefore, basically, it's going to be a summation from the initial state. So, if you look at the numerator in this specific case, from this specific point to this one, this is going to represent basically the Q that we had given for this specific partition function. And this summation sign is going to get for now for the exponents or the logarithms, we're going to have a multiplication being spread across, and they're going to, now suppose I have a into b plus c, or b plus c even as such, there's going to be an element of distributive nature which we're going to see, especially in the natural logarithms and exponents, whereby if we have an addition, we're going to, of course, multiply. If we have a division, we're going to divide in that specific case, but I'm going to mention that one later in a summary of the laws which we're going to use, especially in this specific expression. In this case, our numerator is going to represent this Q, and therefore, if we are going to consider this specific representation, then therefore, that's going to form our first piece of the partition function given as such. Now, before I go into details, I'm going to just mention a summary of a few formulae that we're going to need, and these are going to be from differential calculus, which are going to assist us, especially handle some of the situations which are going to require the concept of differentiation. Now, there are a few rules, especially 4 in nature, which we are going to form a basic, of course, a requirement for us to understand this particular aspect of a differentiation, especially whenever we're going to have various representations for the particular partition function. So the first one is going to be the derivative of this specific power or exponent, or a number raised to a particular power, and that's going to be given in terms of the multiplication of that particular exponential number, or rather the power, and then x, that specific power, and we reduce it by 1. So this is going to imply that we take this specific number that has been raised to form our other power subtracted by 1 given as such. So this is one of the rules that we're going to come across. And then next we're going to have the second rule of a derivative of differentiation of natural logarithms, whereby we're going to have a d over dx over the natural logarithm of x is given in terms of a reciprocal, which is 1 over x, and also that's going to form part of the basis of our rules that we need to understand. Now, in case we have a product of this is going to be uv, the derivative over this specific product is going to be given as one of the elements of that specific product. So we are going to hold the constant one of the elements of those specific product and differentiate the other one with respect to x, and then we're going to have this other element that was differentiated v, and we differentiate the one that was held constant in the first case. So it's going to be du over dx given as such. So this is one of the rules that we're going to see, a product rule which is being applied or applicable in our discussion on the various aspects of our differentiation of the partition function. And also we're going to have the last one perhaps defined from the of course, we have discussed some of these specific differentiation rules in our mathematics lessons, and in this case, the last one that I'm going to define is basically the derivative of a composite function, which is intending the concept of a chain rule. So we're going to have this one given in terms of f, the function of another function y given as such. So the derivative of that specific function is that we're going to derive the first function f with respect to y, and then that's going to form a product with the derivative of this second function with respect to x given as such. So we are going to have this function, a derivative of this function with respect to y, and then we're going to have a derivative over this specific function y with respect to x given in that order, and that's going to form, of course, a specific rule which basically we're going to discuss, or we have discussed in one or another in our concept of the chain rule. And these are going to form a basis for us in understanding the derivative that we're going to come across, especially in the representation of various aspects of the internal energy in that specific case. So catch us in our next video as we're going to look at the second and last aspect of representation of internal energy, especially on the concept of perhaps constant volume and other aspects that we have not touched in this particular discussion. So that is it for now, guys. Bye, God bless you. Catch us in our next video.